So again, build breakers, not gatekeepers. Welcome everybody. Thanks Developers.nl for hosting. And let me quickly introduce myself. Hi, I'm Michiel. I'm a cyclist. And tonight I'm not going to talk to you about cycling, much as I would like. Tonight I'm going to talk to you about something that is very dear to me, no pun intended, traditional software development. Now, traditional software development, for those of us fortunate enough to have lived it, occurs in a number of phases. The first phase of traditional software development is gathering requirements. So what we do is we go to all our stakeholders, we talk to people, we figure out what we need to build, and then we write it up into a big requirements document. Once that is done, we move over to the design phase, where we start designing our software, the infrastructure, the software architecture, how classes need to interact and stuff like that. Once that is approved, we move over to implementing the thing. So we start building our code, writing our classes, building our build scripts, or writing our build scripts. And when that is done, we move over to the verification stage or testing stage, which is where the thing that we just built, we're actually going to test whether it is working, whether it's fulfilling our requirements. And then once that is done, we deploy it, we push it into production, we go live to the customer, and then we go into the maintenance phase. Now, this is, as I said, this is traditional software development, and one big component of this phased approach is that at every step, there is a human gatekeeper or multiple gatekeepers. So there are humans involved in the process that actually that put up gates, that put up fences for somebody to jump across. So, for example, when we do the requirements phase, we first need to build up a list of requirements, and somebody has put some rules for how the requirements document should look. And then we go into the design phase and the implementation phase, and every phase actually is gate kept by one or more persons. Now, those gatekeepers, there's a few problems with those people. Well, not necessarily with those people, but with the roles that they fulfill. And that is, they tend to be silent. So the gatekeepers, for example, people in the testing group, one or two people will be very, very familiar with the system, how it performs under certain conditions, how it reacts to certain inputs, and they will be what we call the local heroes of an organization or of an application. And the problem with that is that because they are local heroes, their knowledge is very contained. And once they would leave an organization or get another role or something like that, they would take all that knowledge with them. And that would hurt the organization. Now, another problem with human gatekeepers and phased approach to software development is that there is a bunch of handoffs. And those handoffs occur at all these different positions or all these different parts in the software development lifecycle. So as we go from one phase to the next phase, we need to hand off our product to the next bunch of people, right? So we have a bunch of people doing requirements gathering, and then they write up their requirements into a document, and then they hand it off to architects to design stuff, to design software architecture and classes and stuff like that. But they were not part of the requirements gathering phase. So they completely missed that context. Now they do their design and they built their design documents, and then they hand it over to a bunch of developers who were not part of the requirements phase nor the design phase. They just have a list of things to build. Then they build things, they hand it over to the QA people who have absolutely no context of all the phases before that. They don't know where the requirements come from. They haven't seen or been part of the design phase, and they sure as hell didn't do any of the implementation. But they are asked to actually verify the application. And then the ultimate handoff is where the application is deemed ready for production and is then handed to operational people to maintain in production. And typically, they are at the end, they are the long tail. They haven't been involved in any of the previous phases, but they are required to maintain that product in production. Okay, so one of the big problems with this phase approach is that it is very costly. Okay, there's from one phase to the next, because of the lack of context, because of the lack of insight that you gather as you go along the way, there's a whole bunch of rework that you need to do, and that's costly. It's also a slow system. As you go from one phase to the next, it's very difficult to take in new knowledge. You would need to go all the way back to the requirements phase, for example, and that makes it very slow and ultimately very wasteful. And what it also, what we've seen in industry is that this system simply does not scale, especially if the competition is doing it differently. Now, what would differently be is doing it in cycles, short cycles. So what we're going to go towards is continuous and many small changes, and those small changes will make sure that we integrate quickly and often, okay? And contrary to popular belief, doing things more often is actually a way to reduce risk, not increase it. So one thing I found on the internet, which makes it true, is this little picture. On the left of the picture, you see an infrequent release schedule. So what you see there is, as you go over time, as you increase time to the right, you build up risk, okay? You build stuff, but you're not actually releasing it to your customers. So you don't know what you are building is actually valuable or is working, okay? You're building up risk, you're building up inventory. That's all you're doing. And then at some point, about halfway in the timeline, you go to production. You try to realize that value towards your customer. And then you find out whether the thing that you built is actually working and is valuable, okay? So you reduce the risk at that point. Now, on the right side of the picture, you have a frequent release schedule, where by doing these many small changes, the amount of risk you build from change to change is very small, okay? So the amount of cost or amount of inventory that you make is very small. And so this leads to the shift left paradigm, where shifting left, when you take a timeline which goes from left to right, we try to position things on the left side, so as early as possible in the development lifecycle. This allows us to eliminate issues early, and why would we do that? Well, research has shown that as far as you go farther into the software development lifecycle, fixing issues, fixing bugs becomes more and more costly, okay? So if we fix an issue in production, it's 30 times more costly than fixing it in the requirements when you're still doing requirements, or 6 times more costly than when you're doing coding. Shift left has also shown that as you go to the left, so more towards your planning and your designing and your development, that the attention to quality is better. Toyota, for example, has shown that quality you can't inspect quality, okay? You can't build a car, and then when the car is built, you can't make it a quality car. The quality cannot be reversed. The quality is built in or it's not, okay? So if you model that, or if you apply that to software development, you need to apply that quality mindset as early as possible. Because if you do that, then the cost of change will remain a roughly linear process, whereas with the traditional way of doing things, at some point you will hit a brick wall. So ultimately, this will lead to higher quality software. Now, you're not here to listen to me rant for hours and hours about agile, lean, and all these things. I'm going to talk to you about a few concrete steps that you can apply to actually implement these many small changes and integrate early and often. So what I'm going to talk to you about is automation, because that is ultimately the key to being this fast, to have this quality under control. Research has shown, for example, in the State of DevOps reports, that high-performing teams have a lot of automation going on in their daily work, in their way of working. With the most important part is an automated build followed by automated unit tests, and we'll come to what those mean. And research has consistently shown that the most high-performing teams have the most automation, especially for the things that require no human involvement. But tonight I'm going to talk to you about a concept called a build breaker. And a build breaker is essentially an automated quality gate. Here's the automation again. And the quality gate has 3 states. It can either fail, it can warn us, or it can pass. Okay? So those 3 conditions, fail, warn, and pass, for a quality gate. And what we're doing with those quality gates is we're going to build them into a thing called a pipeline, a build pipeline. And conceptually, you can see a pipeline like this. We have a developer building some code, you know, typing it in IntelliJ or whatever. And at some point, they check in that code to GitHub, GitLab, and then a process starts running. It starts building the code, it starts testing the code. And once that's all complete, we have a package, okay? This is continuous integration. Continuous integration means I'm working on something and I'm integrating with my colleagues at least once a day to see whether the thing I'm working on actually matches and integrates with the thing the rest of my team is working on. Then we build onto continuous delivery, which takes that package that we built in the build stage, automatically deploys it to a staging or acceptance environment, and then it waits. It waits for somebody to push a button. And when the button is pushed, for example, after we've done some manual approvals or user acceptance tests or stuff like that, then we deploy to production. Code continuous delivery states that code should always be in a releasable state. Okay, so that means I need to be able to go into a team room and say, let's go to production with what we have right now. And then the answer should be, sure, in an hour or so, we'll be live with what we have right now. Not, no, okay, this is going to take us a few weeks to make it stable, and then maybe we can go to production. No, you're always releasable. Now, continuous deployment is sort of seen as the holy grail. The next level beyond continuous delivery is where we actually take that push button away between acceptance and production, and we've automated all those checks. And when those checks pass, well, then every valid commit will go to production. Okay, so this is coming not just from me, but this is coming from people that are knowledgeable about this. For example, Jess Humble and Dave Farley, they wrote the Bible, the book on continuous delivery. And continuous delivery ultimately is about delivering value to users quickly, safely, and most importantly, in a sustainable way. Okay, it's now time to zoom in a little bit on those build breakers that I was talking about. Most of the examples that I will show you tonight will be in PHP, but they are equally applicable to Java, C#, Python, what have you. You know, most of these tools have an equivalent in other languages, in other domains. I will also show some names of tools that you may want to look at some point, may want to discover, and see whether they fit your needs. The things I'm going to talk about happen mostly in the verification stage. And what I mean with that is back to the continuous integration picture. It all happens on the build and test block of the pipeline, essentially. And let's start first with something that is near and dear to most of us and is always guaranteed to trigger discussions: code quality and code standards, tabs versus spaces, indents and stuff like that. Luckily, there are tools for that to enforce it. One of those is simply code styling. Agree on something. It doesn't really matter what it is, whether it's tabs or spaces, whether it's a new line after the semicolon or not, whether it's curly braces on this line or that line. It doesn't really matter as long as you agree on something with your team, and then you can start enforcing them. Then you can start making sure that every new piece of code that is checked in matches the standard that you as a team decided on. And that's cool. You know, for PHP, there's PHP CS, but if you're Java based, then check style with a few different levels that you can choose is very important. And that's the start. Because once we've decided on a code style, then we can start worrying about other things, okay? Then we can start worrying about bugs that we introduce in our code, typing mistakes or other issues that, for example, a tool like FindBugs or a PHP stand or other static analysis tools can find and can warn us about, okay? These are the most important or the most basic parts of actually doing something to your code, but it's not verifying whether your code actually works. So we're going to build in a bunch of tests. Now, over the past few years that I've been consulting at different companies, when I talk about their testing mix, the testing that they do, oftentimes this is the picture that I see. This is what they call the ice cream cone of testing. And the ice cream cone is basically, we have a few unit tests, not a lot. We have some integration tests, also often not a lot. We have a lot of end-to-end tests, but most importantly, or more worryingly, we have lots and lots and lots of manual testing. People actually running test scripts that are written down in Excel sheets or Word documents. And they are manually clicking through things and doing essentially repetitive work every day. How would that look if it were the other way around? Then you end up with the test pyramid. And the test pyramid says that as you go up in the pyramid, costs increase. And as you go down in the pyramid, speed increases. So at the bottom, we have unit tests, the cheapest, fastest, easiest to run and maintain tests. So we have a lot of them. Then we have integration tests above that, which are a little bit more expensive because they require, for example, a database to run, or we need to call to an external service or something like that. So they will be slower, they will be more difficult to maintain. And then at the bottom or at the top, we have end-to-end testing, which is where we require an actual application running because we want to verify the end-to-end test or the end-to-end validity of the system, okay? Also, we need to not forget two important things of testing, which is exploratory testing on and user feedback on one end. User feedback is, for example, a usability form on your system, on your site, that will help you as an early warning, my site is broken, and your customer will actually warn you about that. But also monitoring. Monitoring really is testing, but in the time dimension, okay? Monitoring will alert you to things that maybe your test cannot find out. For example, your site will start breaking under a certain load, such as Meetup just did, right? So one of the things people ask me, okay, what should the mix look like? Well, some wise folks at Google a few years ago said that we are dividing our test mix into three categories: small, medium, large, where small is super fast, medium is a little bit slower, and large are the tests that actually require some time to run. And what they're saying is that the test mix should be 70-20-10. And this is, these are numbers that you hear more often in different contexts, but 70-20-10 basically means we have 70% of our test mix is fast, 20% is a little slower, and 10% are the tests that are the slowest to run. These are not numbers that you should pin yourself on, but these are good numbers to go towards, or at least have some sort of a heuristic in mind. So at the bottom again, unit tests, right? Unit tests should be plentiful, should be fast, should be isolated. I should be able to run my unit test in whichever order and in whichever mix I want. They should not have dependencies on each other. That means that I should be, I should be able to randomize the order. I should be able to parallelize unit tests, and the outcome should not be different. Because if unit tests depend on each other, that's a problem, because then it looks like some test may be leaking state for another test. Okay, so they should be small, plentiful, speedy. And we can also discover the amount of code coverage that those tests are giving us. Okay, code coverage is basically saying to us the amount of executable code or production code that is covered by one or more tests. Now, I've been on projects on applications where 100% was the minimum, and also the maximum, of course, because you can, at least for line-based coverage, you can go over that. For legacy projects, that may be a very different number. I've heard people say 70% or 80%. Now, code coverage, be mindful that it is not a number to chase on its own, because as any metric, a metric can be gamed, a metric can be influenced, but it is something that can have a signal value. For example, if you have 80% code coverage on your system, it doesn't say anything about the tests that make up the 80%. whether they are good or not. The only thing it really is telling you is that 20% of your code base is uncovered by tests, and that may be a danger. Now, if the 20% is trivial code, then that may not be a problem. But if the 20% happens to be your most important business logic in your application, then it is a problem. So use this metric with a grain of salt, but use it as a signal to the health of your code base. Now, integration tests, we can use tools like PHP unit as well as for unit tests, but also tools like Rest Assured or the test context in Spring Boot or in Spring. Integration tests basically allow us to test our code in conjunction with other code. So we have components talking to each other. We have a class talking to an actual database that we put in some fake data, for example, to test whether the loading or the saving from the database works, stuff like that. And then we build up to an interesting stage, which is the acceptance test stage, which is where something called behavior-driven development kicks in. Behavior-driven development, instead of talking in technological terms about functionality, for example, when I click on this button, I go to this page. No, we are talking about the functional domain language. So instead of talking about I click on this button, no, I'm going to, for example, on a search page, on a search site, I'm going to my search results. I'm going on a job site, I'm going to the overview of available jobs in the region of Southern Holland, for example. So again, we're not talking about technical concepts here, but we're talking about natural language concepts. We're talking about business concepts. And we can write those in the given, when, then setup, where given puts our world in a certain state. So let's say I'm on a job site. Well, given that a certain job exists, a certain job offer exists. And when I'm viewing that job as an interested person, then I see a list of related jobs. This is something that is actually more or less a carbon copy of an existing application. Tools like Behat, JBehave, Cucumber allow you to write tests like this and then implement them. And those tests can, look like this, like I should see the last book, and what you write is actually technical code that is behind that statement of natural language. So you actually implement that statement of natural language. Now, some people also do, or instead of acceptance tests, they do what we call UI testing, which is where you have tools like Selenium, for example, or Cypress, where Selenium interacts with your browser or fakes a browser, fakes a user behind a browser, and starts clicking on things. And you program Selenium to, okay, click on this button, then this page should appear. Type in these values in this form, then click on next. It actually simulates a browser session. Those are very useful, powerful, and important tools, but there's one big caveat here, is that because they require a running application and a browser, they are slower, the tests are slower to execute. Plus, if you see something failing here, it's difficult to discover where the failure actually happens. I can describe that by talking about a car, for example. If you were to walk to your car right now and you put the key in the ignition, you try to start and the car doesn't start. Based on just that simple thing, key in the ignition, car doesn't start. Depending on who you are, but for most of us as mere mortals, it will be very difficult to troubleshoot why the car is not starting. Okay, and that's precisely the thing with these end-to-end tests. You're seeing the system as a black box. You're looking at it from the outside. So if you see something 3 layers deep failing, you're not going to see that your spark plug just went dead. The only thing you're seeing is the effect it has on your ignition. Okay, it doesn't work. The car doesn't start. That's all you're seeing. You're seeing the effect of something deep inside the car, inside the system that is not working. That doesn't mean it's useless, but this is something that you need to keep in mind. Now, for those of us that build APIs, contract testing is something that is very useful. Now, contract testing is best described as The folks that have a smoke alarm in their house. Do you have a smoke alarm? Okay. So how often do you test your smoke alarm by putting your house on fire? Never. There's a little button on each smoke alarm, you know, a test button, and you push the test button, and then the thing starts beeping to indicate it's working. Okay. Now that's what we call a contract. We as users of a smoke alarm, we have a contract with the smoke alarm that we test, not by actually doing an end-to-end test, which would mean lighting our house on fire and then verifying that the smoke alarm works. That's very much a one-way street. No, we test that the contract works. So we're testing the testing circuit in the smoke alarm. Now this is contract testing in a nutshell. So when we do API testing, yes, we can test against the concrete API, but let's assume that that API is somewhere not under our control, and we have a network failure, or we have something else. We have situations that are exceedingly rare to occur in practice, but that we want to simulate. For example, AWS going down. We can wait for that to happen, and then that one test will succeed once in a year. But if we do contract testing, then maybe we can simulate that. We can actually verify that the contract we have between an API and us, or between a consumer and our API, is still working. So what one of the tools in this space is doing, Dread, is what it's called is you're writing your API as a blueprint. And the blueprint is basically, if you give me this input, you can expect that output. And that output can be, you can expect these fields with those, you know, this is a string, that's an integer, and stuff like that. That's what you can expect. And that is then your contract, okay? And what Dread then does is, okay, you can spin up a local development copy of your API, the API that you are building, and you're continuously testing whether the responses to your inputs match the contract. And what Dread also allows you to do is actually do that against the production version of your system and continuously monitor whether the responses of your production API matches the contract. So if I give input A, I'm expecting output B back, and that's something you can test in the contract. And then Dread will give you a verdict. Is this API still matching the contract or not? A good example to describe this is, let's say you are building an API and it has a field for date and time, okay? And the field for date and time, in the documentation, it says you can expect a string with the date and the time in the string, okay? But in reality, the API, we are only human, so we wrote a bug, we made an oopsie. Our API actually gives a timestamp, an integer. Now, let's assume we go a few weeks, we go a few months, we don't fix the documentation, we don't fix the API. Now, people have learned to rely on the API giving us timestamps, okay? And that's the contract. So let's say I find out that problem in my documentation and I fix it. Now I'm actually breaking my contract because people have relied on what my API is doing in reality, namely giving me timestamps, giving me integers. And all of a sudden, I fixed my API to give me strings. And all those consumers break. Now, this is something that contract testing can help us support. Another big part of testing in build pipelines is on the topic of security. And this is becoming more important day by day. So one of those areas in security is actually on the level of dependencies, dependency scanning and dependency updates. So one of the things that happens is when we build software, we actually don't build everything ourselves, right? We pull in packages from all over the place, open source, closed source. We pull in libraries, we pull in stuff from GitHub, etc. And so on a typical application, and this is a very benign example, our dependency graph can look like this, or even worse, even bigger, right? For example, if you build something simple in Node.js and you pull in one package, then you tend to pull in hundreds and hundreds of related packages that have some transitive link to what you are building or what you are using. Now, the problem with all these dependencies is not necessarily that they're open source, but that in any of those dependencies may hide a vulnerability or more than one. And these packages are also updated sometimes because of bugs, but sometimes because of vulnerabilities. And we want to be aware when that happens. We want to actually receive notifications about that so that we can do something about it. One of the tools that I'm using a lot for that is called the Panabot, which is integrated into GitHub and lets you discover that some of the libraries, whether it's packages or jars from Maven or PHP packages or Node, whatever, has a vulnerability or has a new version. And then it will actually give you a pull request on your GitHub repository to bump that dependency to a new version that fixes the vulnerability. That's very cool. Now, there are more tools. One of the tools I use a lot as well is called Nexus IQ. But there are more tools in this space, White Source, SNCC. Some are closed source, some are open source. And basically, those tools will scan your all the dependencies that you have in your code, and then give you an alert when one of those dependencies has been found or vulnerable in some shape or form. And then you can decide whether that is something that you need to panic about and fix or not. But it is something that I would suggest putting into your pipeline pretty quickly. Another area of security testing is called SAST, or Static Application Security Test. Static Application Security Tests look a bit like static analysis of your code. And what it does, for example, in a tool called RIPS, it will scan through your code and look for patterns. Patterns such as, are you maybe including application security keys somewhere, access keys, usernames, passwords in your code directly? Are you using SQL injection, or are you maybe susceptible to SQL injection somewhere? So basically, those tools will look for patterns in your code when you may be doing insecure things, if you will. Other tools are in this space are Fortify and SolarCube and Coverity. These tools are very useful, but they have one big drawback, and that's the potential for false positives. And a false positive is best explained by I'm looking at something from a distance, and then it's hard to see what it is. Is it for example, car? Is it a green car or is it a black car? Not entirely sure, but I'm calling it a black car. And as it comes closer, oh no, it's a green car. Okay. And what you have in these tools is also, because they are based on patterns, on rules, that sometimes you may be doing something that is completely okay and is not a security hole or a security leak or a problem. But those tools will think you are writing something that is, their pattern detector detects something. And so the tuning of these tools is going to be very important. Now, for those of us that have GitLab Premium or are using GitLab for open source or for simple projects, GitLab has a bunch of these things built in. So unfortunately, it's only for Premium and Ultimate customers. I'm not affiliated with GitLab, by the way. But in GitLab, you can, if you're interested in that, you can more or less with a few lines of code, you can enable SAST and even dynamic security testing, dependency scanning, and also container scanning, which for us that are doing Docker, for example, is also something that is very useful. Because as we are building more and more stuff, and we're building Docker images and stuff like that, we're also pulling in things that may be vulnerable in those things, right? We're pulling in different versions of Linux or Windows or whatever into our Docker containers, and some of those may be vulnerable. So what we're interested in is, okay, we're building a Docker image based on something that somebody else built, but is that base image, is that image that somebody else built, is that maybe vulnerable, or has something been detected in that we need to know about? And if so, do we need to update? Can we update? Now, there's a few tools in this space called Claire, and one of the more exciting ones is Twistlock. And Twistlock basically gives you all the, or lists all the images that you have, all the images that it's based on, so the entire tree of images, and sees whether there are any vulnerabilities detected and what severity they have. Is this something that can wait, or is this something that needs to be fixed right now? For example, you're pulling in something that contains an SSL vulnerability. You know, a few years ago we had Heartbleed, and we had other OpenSSL vulnerabilities. If you pull that into your image, and then you build an Apache or an Nginx web server with that image, and now you're vulnerable, and you don't know about it because you don't have a scanning tool that's going to alert you to it. So that's something that if you do a lot of containers, a lot of Docker, then I would definitely suggest pulling this into your pipeline. Now, one of the more interesting and also difficult subjects in pipelines and in testing is on the subject of performance. And people have been asking me, okay, I do a lot of load testing on my application, but it happens in acceptance, for example, and it happens on a complete application, on the entire stack. How can I do performance testing in my pipeline? Well, one thing is tooling, of course, and there's a bunch of those. JMeter, Gatling, Locust are some of just 3 of the tools that are available in the space, and there are many, many, many more. But they all sort of do the same thing. We have some sort of a plan or some sort of a script that is going to simulate users, and then, you know, the actions of a user. I click here, I log in there, I do this, I do that. And then we start ramping that up. So now we have 10 users doing this. Now we have 100, now we have thousands. And then we ramp it up until we see cracks appear in our application, and we see where the, you know, where the limits are. But if you want to do that in your pipeline, well, here's a little bit of a recipe that I can suggest to you. Because in a pipeline, you're not concerned about absolute numbers. You're not looking for, does this web service give me a result in 100 milliseconds? No, you're interested in, from this build to the next, am I going faster or am I getting slower? Okay, so what you first want to do is determine a baseline. So I'm running this in the environment that my pipeline runs in. I'm running this bare bones, and I'm recording. Now I have a number. I have a number for every page or every area of interest in my application, a number of, or an indication of its performance. The actual number doesn't really matter, but it's a baseline. And then we start agreeing on some soft and hard limits. So what I mean with that is, when do we want to fail the pipeline? Is that if we go 5% slower, if we get 10% slower, or worse? What is our cutoff? What do we find acceptable, and what do we find not acceptable? And once we have defined that, once we have agreed on that, then we can run this in the pipeline. You know, we build our code, we deploy it in an environment, and then we run that same test that we did in the first step, and then we see whether we are going up or down, and how much. Not in terms of absolute numbers, so we're not interested in the number of milliseconds. We're interested in the degree of deviation in terms of percent. You may want to run this 2 or 3 times to get a good average to account for any oscillation in your pipeline. Sometimes, you know, you're a little bit slower, sometimes you're a little bit faster. Get a good average, and then see over time how that works and whether you need to adjust your soft and your hard limits. Now, there are a few other areas that I want to discuss as we go towards the finish of the talk and towards the questions. Some other areas that you can include in your pipeline to, you know, as you increase your skill level. One of those is called mutation testing. And mutation testing is an interesting field, a relatively new field, I would say, to some degree. Some people may know the term fuzzy testing or fuzz testing, which is a part of mutation testing. Basically, mutation testing, when we do unit testing, we say, for example, I have a routine that adds numbers. Okay, I have a routine or a method, a procedure that adds two numbers, A and B, and the result is C. That's the addition of those two numbers. So 2 plus 2 is 4. Okay, so what we do in a unit test is typically we have a few cases, a few sets of parameters, 2 and 2, and the result that we expect, 4, 1 and 3, 4, 1 and 4, 5, but we're not going to exhaust ourselves and write lines and lines and lines of possibilities, okay? We also probably can safely assume that if we do 1 plus 3 is 4, that 1,000 plus 400 will also work, right? Those are roughly the same numbers. What we're interested in is when I have one negative number and one positive number, when I have two negative numbers, when I have zeros. So edge cases, for example. Now, mutation testing is a tool that can help you find those edge cases and can help you discover whether your unit test will actually work in a large array or large scale, large range of numbers and combinations. Something that I've been working on at my current client is when it comes to approvals and workflows. I'm in the financial industry right now, which means that things cannot always happen without somebody approving it. Now, this is a sometimes necessary step, unfortunately, but we can still automate this as much as possible. What we've done in the pipeline, for example, is call a tool, is invoke a tool called ServiceNow, which is a workflow orchestration tool. And basically what we do is the pipeline submits a request to ServiceNow, and then a workflow is enabled in ServiceNow, and somebody that needs to approve has to do some actions in ServiceNow, and the pipeline is waiting for ServiceNow to give a callback. And once the workflow in ServiceNow is completed, then that application calls back to the pipeline, and the pipeline proceeds. That can work very well. And there's another interesting area that I don't have a lot of experience with myself, but it is on the topic of accessibility. For example, there are tools right now out there, and there's more becoming available in the space every day, to see whether you're building something, okay, and it's visually nice, but if you have somebody that uses screen readers, for example, you know, or they have impaired hearing, and you are using visuals with sound on your website, or people are using magnifiers on their iPhone. What you want is, especially if your user base has a lot of those folks, then you want to test whether your changes are not actually making your site less accessible to those people. And that's something you can automatically, or at least to some degree, test for. And then the last part, essentially, of a build pipeline, and then it becomes a deployment pipeline, is the deployment. And deployments can also work as a build break. Now, one of the most interesting concepts in that space is called the canary, or canary deployment. Now, I'm not so old that I remember the mining business in our country, even though I know, you know, it used to exist here. It used to be quite big. But those guys, what they did was they took animals down with them, right? Canaries, for example, but also other animals. And those animals would warn them when the levels of certain obnoxious gases or deadly gases would exceed the threshold of safety, right? So the canary would die, and then everybody would start running out of the mine. Now, that's a little bit morbid maybe, but it's a good description of what the canary does in IT. So let's assume we have an application, and what we do is the application is connected to the internet or serving users on the internet through a load balancer. And what we do in this situation is initially, my old version is serving all the traffic, okay? Now I'm building a new version of my application, my service. And what the canary is doing is, okay, let's put 1% of traffic, for example, maybe a little more, maybe a little bit less, depends on how much traffic you have. If you're Netflix, 1% is probably too much. If you're me, then 1% is probably good. So you give your new version, you give it 1% of traffic, and then you start checking things like exceptions, errors that you see occurring, Is your server slowing down? Are you seeing problems with memory usage or whatnot? And if you don't see any problems, then you start increasing the amount of traffic to the new version until you have completely moved all the traffic to the new version. And so you do a slow but gradual ramp up of traffic to the new version. The nice thing is, if something fails, then you can start that, or you can stop that ramp up and you can reset, okay? So this is, for example, this is something that Facebook uses. This is something that Netflix uses. Another way of doing, or potential way of doing this is called the blue-green setup. And the blue-green setup basically means we have two sets of infrastructure, two sets of machines or two sets of virtual machines or whatever. One is not doing anything and the other is currently serving all the traffic. And what we can do is we have our old version currently serving all the traffic, we build a new version and we boot that, we build the entire stack, we deploy all the things that we need to deploy, and then we run a few tests, but it's not doing any, it's not serving any traffic. And then when we're confident, when we have a feeling that, okay, this can now go, we flip the switch and we go to the other set. Now, if we see something failing, we can immediately flip back to the other, right? The only thing that we need to be aware of in the pipeline is where are we? Which of those two is the blue active or is the green active? Because it would be problematic if we deploy to the active set in this case. But the blue-green system can be a safety measure as well. So a few tips as we're rounding up. One thing that you need to be aware of, all these different types of testing that I introduced and that I talked about, we can do, we can build all the tests that we want. The thing is, testing ultimately is a form of risk management, right? We can test for everything. Well, no, we can't. Cue the Titanic. We can never test for anything. We can only test for the things that we know, right? Testing is verification. Testing cannot tell us the things we don't know because we haven't built them into test yet. Or does no test suite detects every issue? That means something, which I'll come back in a little bit. Also avoid flaky tests. A flaky test is a test which fails when the production code it is verifying is actually working. So a flaky test could be, for example, because of a network issue or a timing issue. Who here had a test fail when we switched from winter to summertime or vice versa? I've had that happen to me. Those are flaky tests. The code that it is testing is probably fine, but the test bailed on us. And if we don't watch those, then those tests will become tests we're not trusting. And if we have a lot of those, then we stop trusting all the tests altogether. The key to all this is watch your build time. Like I said, we can write tests until we go green, but that's not the point. Because if we have a build time that is very long, then people will start either ignoring the build or they will adjust their own speed to match. Both are not very optimal. So the pipeline speed to me is key. One of the people in this space that I respect a lot, Paul Hammond, he wrote the book on trunk-based development. He says that 30 minutes from the start of the pipeline to the deploy to production should be 30 minutes at most. I have a little bit higher bar than that, 15 to 20 minutes, that's my personal max. So the past 50 minutes or so, I've been talking about build breakers. Those build breakers are not to be used in isolation. They are, however, to be used in pipelines. And these days, when it comes to GitLab and Travis and Jenkins and all the other good tools that we have in this space, we can write our pipelines as code just as much as all the other code that we write. And when we do that, we get nice overviews. We see where builds are failing. We see why builds are failing. Builds fail quickly and give us fast feedback. And those builds build up an audit log. They build up a log of what happened, where it happened, when it happened. And that's very interesting because that visibility gives you insight into what you're doing and how you're doing. And I want to close off with this screenshot from one of my earlier projects, which is a production pipeline which ran about 20 minutes from start to finish. So from the code checked in, the build being started, to the last deployment and production finishing, took about 20 minutes. Now, the fast feedback that I was talking about, if that happens, you need to know about it very quickly. So whether it's sirens, lamps, hallway monitors, Slack notifications, push notifications on your phone, USB rocket launcher with Nerf darts, something that triggers your developers, the people in your team, to focus on fixing that build when it breaks. Now it's time for you to start working on this. First, agree on standards. So agree on what are your soft and your hard limits? What are we starting with first? What is our code style? How do we want to define our test mix? And then start building a pipeline. Start shifting left your testing activity and your quality activity. Most of all, take small steps, many small steps. And over time, adjust the strictness of your pipeline. Instead of warning on things, start failing on things. Increase the bar for your code coverage, increase the bar for your check style warnings, and make your pipeline stricter. And let's all turn those gatekeepers into build breakers. Now, I wish you all the best of luck. And as you are doing that, here's some literature that I want to give you to read up on. The first book I already mentioned, Continuous Delivery by Jess Humble-Dave Farley. And in the middle is The Science of DevOps, Accelerate, which is a very interesting book which describes all the research from the State of DevOps reports. And then on the right, we have Measuring Continuous Delivery by my good friend Steve Smith, who discovers and who describes how you can measure your path toward continuous delivery. So how are your builds doing? How often are you failing? How quickly are you fixing your builds? Metrics that are interesting to see how far you are on your continuous delivery journey. Now, if you want to reach out to me, I'll be here a little bit for some questions through a Zoom chat, but you can also reach out to me later through Twitter @MichielTCS. My email address is there as well, and on my website, I blog about this subject and other subjects as well. Thank you for listening, everybody, and let's go take a look at the chat to see if there are any questions.